takes a particle into its own antiparticle. Yes, if you want to say it that way, yes. However, in the when this is used in practice is one usually says, let us assign the new left and the new right to the leptons and both of them the antiparticles to the anti-leptons. But you're right, you could technically, if you just had the sterol off by itself, completely isolated, no couplings to anything else, then it would make more sense to say what you're saying. Okay, now you can put these together, of course, with one sterol and one active to make a 2x2 mass matrix, which is of the form nu bar C left, MT, MD, MD, MS. So this is nu C right, plus Hermitian conjugate. So if I introduce both, I could have all of these present simultaneously. If I introduce, two, an active and a sterol. So MT would be the Majorana mass term that couples this to this, plus its Hermitian conjugate. The MS would be the sterol case that connects this to its CT conjugate. And the Dirac term, well, I got a 1/2 here, MD, and it's nu bar left, MD, nu C, nu right. And then there's a 1/2 of nu bar C left, nu C right, and it turns out there's a simple identity that nu bar C left, nu C right is just the adjoint of it's just the equivalent to nu bar right, nu left. So you could have both present simultaneously. And if they are all there, or several of these are there, you can have, well, if they're all there or some are there, in general you would have to diagonalize this. It's a mass matrix, and we always have to diagonalize mass matrices, and there would be two mass eigenstates, which in general would be two Majorana mass eigenstates. There are several important limits. There's the pure Majorana, MD equals 0. The Majorana mass is pretty active and sterol. Of course, in that limit, one doesn't necessarily even have to introduce the sterol component. There is the pure Dirac, which is MT equals MS equals 0. And then, although it would be written in a sort of funny, non-conventional form, it is indeed, does reproduce the Dirac case. And nu right goes to nu left, and nu C right to nu C left, so there would be a disturbed lepton number. And I'll just say in passing, I said that generally this matrix has two eigenvectors that are Majorana mass eigenstates. One can actually think, I don't want to develop this, but you can actually think of a Dirac neutrino or a Dirac fermion as two degenerate Majorana states. If MT and MS were 0, then clearly that matrix would be like 0, 0, 1, 1, and the up cosine, the two eigenvalues are the same. So you can actually think of Dirac neutrino in some sense as two degenerate Majorana neutrinos with opposite sign for the mass. The sign of a fermion mass can always be made positive by redefining the phase of one of the components. Okay. However, I want to mention the seesaw limit. And I'll call it the type seesaw. What I'm going to describe is often called the seesaw. Last time I actually used the word seesaw in connection with that higher dimensional operator and said that anything that looks like that is a seesaw. Some people use the word that way. Some people use seesaw or type 1 seesaw for the specific model that implements that higher dimensional operator, which I will now describe. So this is the limit. One usually takes MC equals 0. So there's no Higgs triplet, for example. And MD very much smaller than MS. So in other words, one has a mass matrix 0, MD, MD, MS, where this sterol Majorana mass term is very, very large. And MD is then going to be taken to be similar to the quark or charged lepton masses. Sometimes it's taken to be like the quark masses, sometimes like the charged lepton masses, but not, so it is generated by the Higgs triplet, but without particularly small Yukawa. The large MS is due to the fact that if, for example, it's generated this way, this Higgs singlet may be associated with some very high-scale new physics, perhaps 10 to the 14 GeV or something like that. Well, in that limit, it's easy to diagonalize this matrix. The eigenvalues are M1, rho 1, is equal to minus MD squared over MS, and M2 is approximately MS. These are not exact, but I mean, it's incredibly good approximation. And so you have one very heavy state, which is Majorana, and which is almost entirely associated with that sterol neutrino. And then you have one very light state. It's called a seesaw because, again, it's a normal direct type mass times mg over ms, so it's inversely proportional to the big scale. Yes?
How do you solve the change when you have degeneration?
Yeah. Let me just come to that in a moment. Here I'm just talking about one generation, and but I'll come to that for in a second. Okay, so first of all, so this is a way of getting a very small mass eigenvalue out of a very sort of normal Dirac without having to invoke a small u power and having some underlying new physics that is very large. The light eigenvalues, I could have put zeros on here to indicate that these were the sort of weak eigenstates. The mass eigenstate associated with the light one is just nu L0, and then there's a correction. The first correction would be md over ms times the sterile. So indeed these eigenvectors are linear combinations of the sterile, but in the limit I'm talking about this is negligible. So this is a concrete implementation of that more general seesaw, and you can think of it diagrammatically. That diagram up there can be thought of just as nu c right, and then there's a Higgs and some direct u-power, so that md is hd nu, and then this is nu c left, and here is the ms, and then here's nu left, and here's nu right, and nu. So in other words, the active right-handed turns into a sterile left-handed by a normal Dirac type interaction with the Higgs, and then there's a very large Majorana mass a very large Majorana mass insertion that takes the nu c left into the nu right for the sterile, and then you turn it back into a nu left. The lepton number violation is all right here, and this is just a, you put a circle around all of that stuff. It's just a concrete realization of that more general blob up there. This is the sort of canonical seesaw model, and it's very nice in the sense that it's kind of elegant. The sterile neutrino can actually play a role in cosmology, and the CKs can be associated with the matter-antimatter asymmetry, and so many people favor this as the model. There are other implementations of the seesaw model that don't involve right-handed sterile neutrino, which instead involve some spin zero field or the excitations associated with a string theory, but this is the most popular. Now, for your question, the simplest way to extend this would be, the three families, would be to say that there's three of these and three of these, and that each of these blocks are 3 by 3 matrices. And if you say that the three eigenvalues of this one are all very large, then you just get 3 light sterile neutrinos, active neutrinos, and 3 heavy steriles. Okay, any other questions? Of course, I should say that there are in-between cases, either in the 6 by 6 or the 2 by 2 case, in which the steriles are, in which you just have two combinations, and that's not the seesaw, and those in-between cases have been suggested by some experiments, but as of now, it's not at all clear that that's the case. Yes?
What implications do you have for setting MT equals 0?
Well, it depends on your underlying theory. Remember, I said that MT violates weak isospin by 1 full unit. So if you don't introduce an elementary Higgs triplet, it will be 0 to begin with. I mean, if the only ingredients you have in your theory are the Higgs doublet and the sterile neutrino and whatever gets the sterile neutrino a big mass, then at the normalizable level, MT is 0. Now, once you go through all this business, if you say, well, the sterile neutrino is now extremely heavy, and I'll just ignore it and treat the result of this diagram as some effective term, it looks like the MT term. However, there are models in which MT is not equal to 0, and in that case, what you would get is this. And so you would have to be consistent with when we know this would have to be independently small for some other reason other than the seesaw. And there are some grand unified theories in which both mechanisms occur simultaneously, and in which DMT is associated with some Higgs triplet, and which is sort of natural that they're both small. So there's lots of possibilities. We don't know what the scale of the MS is. If you take MG to be like the top quark mass, then MS could be 10 to the 14 GeV. On the other hand, if you take MG to be like the electron mass, then MS could be 100 teens. So it could be anywhere in between. And there are all kinds of models exploring every possibility and every variation. Let us suppose that we have somehow 3 write active neutrinos, and for the rest of the discussion, or most of the rest, I don't care whether they are Dirac for some reason, just small Dirac, or whether they're small Majorana, such as by a seesaw. It doesn't matter from now on. Let's just say I have 3 very light neutrinos. In that case, let's come back to our weak charge current, the leptonic part. And here, by the way, I'm writing the lowering operator. I usually write the charge raising one, but I'm going to write the charge lowering operator. This becomes E bar, U bar, tau bar, gamma, mu, 1 minus gamma 5, times GL, the dagger now, since I missed the other current, U1, mu2, mu3, where these are the 3 mass eigenstates. And the VL dagger, which is the AL E dagger, AL mu, is simply the analog of the CKM matrix, but now in the lepton sector. And for some reason, it's sort of conventional to write all this stuff for J for the leptons and the J dagger for the quarks. That's a historical accident. And this matrix is called the PMNS matrix. And after the people who wrote it down, it's the Antacorvo, Maki, Nakagawa, Sakata. And I'm not going to write it out because that would take me 2 minutes to write it out. Okay, so now again, just like in the CKM sector, there are various parameterizations of this. But I'm going to write this CL dagger as, again, the product of matrices. So again, Sij is the sine of some angle. These are not the same angles as in the quark sector, they're completely separate. But I'm not going to introduce yet more complicated notation. And then 2, 1, 3, 0, 1, 0, 0, 0. So that's like similar form to what I wrote for the CKM. And then there's possibly another term here. And this other term is the diagonal phase matrix. And let me defer the discussion of this for a moment. This is Majorana only. So no, let me not defer discussion. Remember, I counted the phases in the CKM matrix, and I said that I could remove 5 unobservable phases by redefining the phases of the 6 quark states, and only the differences entered, so there were 5 that sort of disappeared. If I have Majorana neutrinos, they're not 6 independent states, there's only 3, because the anti-neutrinos are just the right-handed, are just the CP conjugates. So I don't have, I can't remove 5, I can only remove 3 of them, it turns out. And so there are 2 extra phases that come in that correspond to systems that are now in principle observable phases in the Majorana case only. However, I want to focus more on the rest. I mentioned the atmospheric neutrinos yesterday. This is a term that is dominantly associated with the atmospheric neutrinos. And unlike the quarks sector, in which all the mixing angles are small, this mixing angle is actually rather large. The S squared 2, 3 is somewhere between 0.35 and 0.65. That is, it's large. It's not a small quantity. That's the square of the side of the angle. And we'll often talk about the maximal mixing, will correspond to S squared 2, 3 of a half. The maximal mixing is pi over 4 in angle. Half. At one time it seems certainly that this was actually maximal, but probably it's a little away from maximal, but it's very large. I mentioned the solar neutrinos yesterday, the neutrinos from the sun. This is, first term largely drives the solar, and here the S squared 1, 2 is also large, but it is not maximal. It's around 0.3. This term involves a third angle, and this third angle is small. So both have 3 small angles. Here we have 2 large angles and 1 small angle. It's only the last 3 years or so that we've actually been able to realize that this is actually non-zero. It now seems like the S squared NP is about 0.02. That's 1.3, not 1.2, sorry. And this comes mainly from reactor experiments. Notice that having the non-zero S13 is essential if you're going to measure the delta, the CT violation phase. It would just go way beyond observable. And that's because if S13 were 0, effectively any process would be like 2 neutrinos mixing, not 3. We need to have all 3 play a role simultaneously to have CT violation, at least from this delta. The delta is not known yet. There's some slight hint that it's around 180 degrees, but it's far from conclusive. Yes.
So, you might like to review the method and put that diagram for generating mass. Where it's right above the next piece where the dash circle neutrino is CC here.
It does not matter for the present purposes whether the neutrinos are Majorana or Dirac, because it's really only the say the new left that into the weak interactions. And so it really doesn't matter whether the right-handed partners were sterile or active, except for these extra phases here. If there were new interactions that involved V plus A, then things would be more complicated. Okay, let me say a little about now the experiments on this. There are, of course, many types of experiments. And first of all, new counting. In nu equals the number of light active neutrinos. And we all know now it's string. But it's really an experimental question. And this comes from the Z decays. The Z can decay into nu I left, nu I left, nu bar. It can decay into any active neutrino, and so if there were, well, you can't observe directly in the detector the Z decays, but you can observe the cross-section for E plus E minus goes to, say, hadrons, and it's a typical Wright-Wigner sort of thing, peaked at the Z mass, and with some width is the total Z width. And one can measure the total Z width, and one can also measure directly the amount of hadrons and charged leptons produced, and anything else. So the gamma for the width for C to decay into nu bar is the width from the line shape minus the observed width into LL bar minus gamma C goes to hadrons. And the bottom line is that nu is experimentally 2.985 plus or minus 0.009. Consistent with 3, it's not 2, it's not 4. Incidentally, if there were other stuff produced in the Z decays that didn't show up directly in the detector, they would also contribute to this number in an additive way. So this actually includes a lot of things. So there's only 3 active neutrinos. The next question is Majorana versus Dirac. And seesaw, I count as Majorana here. Well, there's only one practical way. You can draw all kinds of processes that in principle would distinguish, but there's only one in practice, and that's neutrino-less double beta decay. Zero nu means this is double beta decay without neutrino emission. This is the process NN goes to PP.